after that nice talk by Christopher, I'm going to give you a perspective about how we look for mergers in the gravitational wave data from the LVC that the LVC releases and what we learned from it. So at the outset, I'm not speaking for the LVC. So if I say something incorrect, I'm responsible for it and not the LVC. So with that, yeah, so since most of the participants of this conference are like experts in gravitational wave modeling from the theory perspective, I thought I'll give you a slightly like sort of in the weeds look at how we use your waveform models that you generate and find events, right? Which maybe you don't usually see. So this is sort of a rough schematic view sort of the process of going from the raw data to astrophysical conclusions. So, we start with the raw strain, the D of t that we get from the LVC, which on the top left, and then we have to build a signal model. So this is where the theory comes in. So you have a space of signals with a bunch of, with a set of allowed parameters. And then for each value of the parameters, you have a signal that you have some confidence about it from how that theory predicts that the signal is of this form. And then we go out, take that model, and we search for it. And I'll describe the process of the search in the next few slides, but essentially the point is you can think of it sort of like a particle physics experiment where you have some target, and then you do some data analysis. You get a set of what you would call triggers here. So here the triggers are like places in the gravitational wave data where some summary statistic that you have constructed is above some threshold of significance. And then you understand the distribution of the triggers in the null case, where if there were no gravitational waves in the universe. And then you also look at this the distribution in the in the actual case. And then if you have signals in the data, they would show up as outliers, like like in the hump there. So those are the gravitational wave signals that are in the data. And then you go out and then you go take all of those signals or all of those candidates, which would be more appropriate at this stage. And then you infer parameters using Bayesian parameter estimation, which Christopher talked about in the previous talk. So you get a bunch of posterior distributions for each event, which are with some confidence intervals on the underlying parameters. And then you take all the individual events together, and then you look at them as a collection and try to infer not the properties of any individual event in particular, but like what is the distribution of these events out there in signals in parameter space, and are there any interesting features, and what does that tell you about how these events might have been assembled, right? So this is the entire process, and different parts of it are sort of carried out by different people usually, but this is the entire chain, right? So I don't need to get into this for this audience, but usually, so the signal, so the bare properties of the signal, you can just get it from sort of Newtonian light physics with some extra additions, which is the quadrupole radiation, which drains energy away from the system. So the typical amplitude of the gravitational waves for a signal, which is like the first event that you saw, 150914, is around 1 part in 10 to the 21. And so the frequency chirps with time in the manner that we all know. And for these heavy signals, which are the majority of the signals that we have seen, the signals are very short, like typically a few 100 milliseconds max in the gravitational wave detector. And this is set by the minimum frequency that your detector is calibrated and usable, right? So if you keep reducing the minimum frequency, the signals get longer and longer in band. And finally, the details of detection depend on what is called the orbital phase, which is roughly the, like you integrate the number of cycles that the signal, performs while it's in your band. And that's typically some power law as a function of frequency. And in the frequency domain, in the stationary phase approximation, the waveform typically have a power law as a function of frequency in their amplitude. And then there is a sharp cutoff when you start seeing when you start approaching the merger that we all know. So these are the sort of the bare bones kind of signals that we are looking for. And how do you go about looking for such a signal in the data, right? So you have some data which is here. You can see that the typical amplitude is 10 to the minus 18. So it's formally 3 orders of magnitude louder than the peak of the amplitude that you see. So you can't find these signals by eye usually. So you have to build a noise model. So the noise model, the textbook or the standard noise model is that the data is stationary Gaussian noise. So that is, its statistics are completely known once you know its autocorrelation function, or equivalently its power spectral density, which is this S of f or sigma square of f. And even though the experimentalists have carefully designed the experiment, like they cannot tell you what S of f is. If you're analyzing the data, you have to measure it for yourself. And okay, so once you have identified this noise model, then you go about constructing a summary statistic, which is, so I think Christopher touched upon it in the last talk, where we essentially first whiten the data, which is we get it to the point where all the frequencies have the same RMS. And then we also whiten the template, which is the gravitational wave, like signal model that, say, a theorist has given us. And then we convolve the whitened data with the whitened template. And if your model of the noise is correct, then this convolution should behave like a signal to noise ratio. So that means its statistics are known that it has some exponential distribution, right? And okay, so now you have 2 detectors. So you have, let's say, Hanford and Livingston in the first run, and now you have Virgo. So you have some more information than just from what you would get from a single detector. So then, in the case when you're analyzing Hanford and Livingston, for example, the astrophysical signals have a time delay which is bounded by roughly 10 milliseconds, depending on where they come from the sky. So this also gives you a neat way of estimating your background empirically by shifting the detector streams by more than 10 milliseconds. And then any coincidental peaks you get are background. So then you estimate the statistics by doing these time slides. So this is there are other ways of doing it. This is an easy way of doing it, right? So, okay, now you have a background model that you have an empirical way of constructing a background model, and you have a bunch of triggers, right? That are where you have this SNR is high, right? So now you have to have some criterion for calling something an event, or more correctly, a candidate. So there are 2 criteria that the LVC has defined. So the first criteria is maybe more familiar to a particle physics experimentalist, where essentially you look for outliers in your detection statistic, and the outliers have a significance determined by how far out they are in the tail, and you can give a false alarm probability. Or in this case, since you can keep running the experiment for a long time, you have a false alarm rate, the rate at which you get triggers above some significance, above some value of the statistic. But then the second statistic that people use here is sort of unique to gravitational waves, or unique to an astrophysical system, is because these things are always happening, right? The nature is throwing more and more of them at you over time. You can imagine that, like, if you reach a point where the events are like rain, they're just coming in all the time. So then the significance might not be the best thing to use to call something an event. You would rather compare the signal hypothesis and the noise hypothesis. So you ask for the rate at which nature is throwing these raindrops, and you ask for the rate at which the detector is throwing them out, and you compare them. And this relative rate is quantified by this probability of astrophysical origin, which is what the LVC calls P astro. And the criterion is this P astro should be greater than 50%. This is what Christopher also mentioned in the previous talk. So these numbers have sort of changed over the run, but their meaning is the same. Okay, so now given this simple picture, when you go out and actually do this, then you see some practical complications. So the first thing is that, of course, you have not just one event, but you have events from a range of parameters. So you have to build what is called a template bank. So you have to you can imagine that if you're fishing, you would make a net, and the net sort of coarsely covers the allowed region such that any event or anything would sort of not fall between the cracks, not fall between the the threads of the net, right? So you try to, with a desired amount of with a desired amount of fidelity, you can make the net as fine as you want. So this is a template bank, and different searches have their own template banks, where the template bank is typically either a regular grid or a random grid in the space of parameters that you're seeking to explore. So one interesting thing that we see is that most detections happen when the net, where there are very few templates comparatively, while most of the templates are concentrated towards regions with few detections. And this is a feature and not a bug. And that is because if you ask roughly what is the criterion to place a new template, you ask that, whenever the gravitational waveform completes more than a quarter cycle, then you lose fidelity to the signal. So then you place an extra one. So then if you ask how many cycles does the waveform complete in the band, it's a very steep power law of the mass. So at the low mass end, you're forced to place many more templates, even though you are actually detecting fewer things there. So this is not a feature of physics, or sorry, astrophysics, but a feature of physics, right? Which is just saying how the signal space behaves. So if you don't account for this, you would immediately, you can sort of see that you will take a sensitivity hit in the heavier region of the template of parameter space, because the outliers there will be overwhelmed by the lighter region, right? Where formally, they might not even be coming from the same sort of astrophysical distribution. So, or say, same origin. So in the first runs, when comparatively little was known about the astrophysical distribution, everything was sort of put in one bucket. But as we had more and more detections and our understanding of the astrophysical population evolved, then you would want to use that to sort of not take a sensitivity hit where you are seeing most events. So one way of doing that is to downweight the templates at the low mass end, because there's just too many of them, not for an astrophysical reason. So this is, this was suggested and is now implemented in the most recent LIGO Virgo searches. And so so in our search, what we do is we sort of divide the search into a bunch of sub searches, each of which spans roughly the same logarithmic range in mass. And we treat each of them as a different search, like they are searching for different things. And in this way, you get a number that for each search that is not affected by the multiplicity of templates in another region. And if you want to give yourself a penalty for looking for another region, you can downweight it yourself. Right. So this is one thing. So one feature of doing it the first way is that the number, so the false alarm rate is a extensive quantity. So it depends on the entire search. So imagine you go back and add some extra parameter space because you got some new waveforms and you want to search for it, then it will formally change the numbers for every other thing that you found previously. And I would not like to retroactively change things. So I make them, so we sort of make them into separate searches. Okay. So that is one sort of simple thing. But then the second thing is you're immediately hit by the realization that your simple textbook model of the noise is incorrect. It is not really Gaussian random noise. And how do you see it is, so we have this train, and you can, if really the detection statistic behaves like an SNR, then it should have some unit variance. So you can take different chunks of data and measure the variance empirically. And you can ask, what is the distribution of these variances that you empirically measure? And you can predict either theoretically or empirically how it would behave if it were truly Gaussian random noise. And in reality, you find that there is sort of a heavy tail. So the variance is not really behaving the way it would. So then the realization you get is that this comes from the fact that you're assuming that the data is stationary Gaussian random noise. So it is So the autocorrelation function is just a function of the lag. So in reality, what's happening is approximately that the autocorrelation function has a fast behavior and a slow behavior, where on very long time scales, where by very long I mean tens of seconds and all the way down to few seconds, the autocorrelation function is slowly varying, but within this region, it is more or less stationary. So once you have this, then you can try to account for this. So this is one effect. And then the other thing is a more sort of ugly effect of non-stationarity, which is that there are all sorts of these glitches because the detector is misbehaving or nature is throwing things at the detector which are not, gravitational waves. And the result of this is that when you actually make a distribution of the background that you empirically measure, it deviates from the Gaussian form both in the core and in the tails. And then, but once you know it, you can try to account for this. So you can account for the incorrect PST and you can account for the glitches by sort of trying to design vetoes like LVC, like even a particle physics experiment, you have vetoes, right? So you try to design vetoes. And one interesting thing is that the rate of glitches, it seems to know about the parameters in the sense that, well, it's not really that the glitches know about the parameters, but some gravitational wave waveforms are better at mimicking glitches than other ones. So in particular, the heavier region where you see most of the events, unfortunately have the highest, similarity to glitches. So you have to sort of aggressively remove glitches in order to be able to see the heavy events, even though from a Gaussian noise perspective, you have a lot of sensitivity there, right? Okay, so after all of this, so you can imagine that, this procedure is way more complicated than the simple Gaussian noise picture that I laid out in the beginning. And anyone who embarks upon this endeavor will have to make a lot of choices. So in particular, within the LVC itself, there are multiple teams that independently sort of do the search. And each team has made their own choices. So hence, I'm not expecting you to read all of these numbers, but within the LVC events, like when you say something is an event, you will find that, like they have multiple analyses whose results are reported concurrently in the same paper. And for most of the super loud events, all of the analyses agree. But as you get down into the bulk of the distribution, you will start to see cases where the analyses don't agree. And this is to be expected because, like ultimately you're sort of, when you start to go down in sensitivity, how you treat the noise starts to make a difference. But most of the events, like the loud events, are very secure. But then when you get into the bulk, the numbers can have to be interpreted with this in mind. So ultimately, there is a criterion for making it into one of these lists, which is that one of the pipelines assigns a probability of astrophysical origin of greater than 50%, and there is a cut on false alarm rate, which is that it should happen less frequently than roughly like twice a day. This is the number in the latest paper, right? So in our search, we sort of, since we are not really in the LVC, we sort of took the data and with an open mind just started to reconstruct our own search, or rather construct our own search. And we developed several tools that we borrowed ideas from, let's say, other fields like in cosmology, and improved the search, at least in our way of looking at it. And I'll just briefly touch upon this and then go to the astrophysical results, which is that, regardless of whether you think, something is correct or not, one way of testing it is just look at the background. Like if your analysis improves the background, like if the rate of background triggers is lower, then your analysis is more sensitive. So this is like a statement that is relatively uncontroversial. So this is showing the level of the background. So in each detector, so rho square is the signal to noise ratio square for and the y-axis is the number of times, or the rate at which the analysis throws out triggers at this level of SNR square. And by applying each of the improvements that I mentioned, so the PSD drift correction is talking about the non-stationarity, the slow non-stationarity, and the V2 is talking about how we deal with the glitches. And by cumulatively applying this, we get pretty close to the Gaussian case, which is so the green line is not quite Gaussian, but it is getting close to it. And obviously the curves differ depending on the region of parameter space, because as I said, the glitches are better at mimicking the heavier region than the lighter region. So what I call BBX30 is the heavier region, and what I call BBX00 is the lighter region, which are like the mass gap events, while the heavier ones are like 150914 type events. So for the heavier ones, you can see that if you don't treat the glitches, you are just overwhelmed by the by the glitches there. And for the lighter ones, the effect of the non-stationarity is more important, for the mass gap or the low mass events. So you have to sort of have an integrated approach to improve the sensitivity in all regions of parameter space. And we can also see this so this is showing, so earlier I was showing a 1D distribution. So the top plot is showing the background and the events that were detected in the space of so the x-axis is the SNR square in Hanford, and the y-axis is the SNR square in Livingston. And the gray region, which I don't know if it's very visible, but that is where the background. So these are all obtained by taking time lags of more than 10 milliseconds. And, like every time you get something that flickers, then, you count that as a background. And you can see that by applying the sort of the glitch detection and by improving the data analysis, we can get the background, like we can really significantly reduce the background. And in particular, the blue dots are the very confident, LVC events that are in there. And you can see that some of the events, they have some background above them. So they have some false alarm rates. And after we do this improvement, like for many of these events, we can only get like an upper bound on the false alarm rate because there is no background above them. And we can also test our code by performing injections by adding fake events and seeing that we can recover them. So we also do that. And okay, I'll skip this. How much time do I have left? Just checking. Okay, so I'll skip this. Okay.
Yeah, you have 7 minutes.
Okay, thanks. So one thing also that we did, which is kind of, I think, new, is we sort of tried to reconstruct the optimal way of combining data from multiple detectors to get a statistic that carries the most information about an event in there. So from sort of theorems in statistics, we know that if you had infinite computational power, the thing you would compute is what you would call the Bayesian evidence, right? If you have an event and you get a signal in Hanford, a signal in Livingston, and a signal in Virgo, what's the optimal way to combine them to get some number? And this is what is called the Bayesian evidence, which is the product of the prior and the likelihood that is integrated out. So this is the denominator in the formula that Christopher showed in the previous talk. So for various reasons in the past, pipelines or analyses have, at least in the search phase, have not really dealt with the complete evidence because it's kind of hard to do. And you only can touch it during the parameter estimation stage where you infer the parameters of the events. So here we sort of managed to figure out a clever way or a quick way to sort of marginalize over all the extrinsic parameters. So the extrinsic parameters are not the masses and spins, but all the other parameters which tell how the merger is oriented and arranged relative to you and where it is, right? So like the inclination, the orbital phase, the sky location, the polarization angle, and the distance and the time. So you have to marginalize over all of these. And so we found some way to sort of analytically marginalize over some of these parameters and find a fast Monte Carlo algorithm to simulate over the other things, such that we can compute this quantity not only for the events but also for all the time slides, right? For all the background, and in this way we can improve the sensitivity. And So one way of thinking about it is, so this thing is it depends only on the signal to noise ratio as a function of time in each detector, and then you do some integrations over it. So the simple way to do it was, in the past, was take something that depended only on the peak value of the signal to noise ratio and some phases, but this thing is formally giving you something that's a function of the entire time series of the signal to noise ratio. So this is like doing a parameter estimation. So by having these improvements, we sort of ran our analysis on both O1 and O2, which presented in the past, and also for O3A recently, where so the left-hand column shows the results of our analysis on the events that are in the tables presented by the LVC, and the right hand is the new candidates that popped up above the threshold of significance that I talked about earlier. And so these new candidates have obviously various levels of believability, right? Because they have various levels of probability of astrophysical origin. So they're all formally above the p astro of a half cut, but not everything with a p astro of half would be something you would bet your life on, right? So there's a varying level of certainty in the reality of these things, just like in the official analysis as well. And the most interesting ones are, so the most interesting signals, it turns out like they show signs of higher harmonics. So which is kind of a surprise, or well, not really a surprise, but it's kind of unexpected from the search perspective, because our search only included the dominant quadrupole harmonic of the signal as in constructing the statistic. But now we find things where it's fairly after the fact, when we analyze the data with a more complete waveform model, which includes not only the 2-2 harmonic, but also the higher harmonics, we find evidence for higher harmonics in the top 2 events, which are the most significant ones, and in fact also signs of precession, orbital precession, which was not included in the search. So I mean, this is interesting, but also it tells us that there is more to get out of the data, right? Okay, and then we also find events which have masses in the lower and upper mass gaps that Christopher talked about earlier. So there is an event with so these are showing the inferred parameters of some of these events in the space of the source frame mass of the primary and secondary black hole and the effective spin parameters. And so this one has a mass which is sort of spans the range between the upper range of the binary neutron star distribution all the way to the lower range of the black hole mass distribution. And we also see one where the M1 is, it has a distribution that is broad, centered at around 70, with a width of a few tens. So these are kind of interesting events. And okay, so this is the search. And we also did a population analysis, where this population analysis was done not on our events, because this was at the time we did this population analysis, we did not have our search, we did not finish running our search, but we did our population analysis on the LVC events, which were already released, which the LVC also did. But sort of we just wanted to just wanted to see for our own eyes what is happening in the data. So okay, this is like so we found an interesting conclusion. So this is like sort of the dumb or the quick way to get this, to see that there is something interesting, which is, so this is looking at the effective spin parameter, which is often the quantity that is most well measured with respect to the angular momenta of the black holes. And this is taking all the events in the LVC catalog, and it's looking at, so this plot is for each event, it's taking the best fit value of chi effective and dividing by the uncertainty in the inferred chi effective. So this would be like the measured chi effective divided by its error. And we are sort of sorting all the events by this number. So if all the events were drawn from a chi effective from an astrophysical population with chi effective equals 0, and the only chi effective you measured was because of measurement noise, then you would expect that they would be distributed like a Gaussian distribution, cumulative distribution. So those are the black lines.
Teja, sorry to interrupt. You may want to wrap up also.
Okay, yeah, this is actually my second last slide, so I just finished. And even after, so we see an excess at positive chi effectives, and this analysis on the left is not exactly morally correct because there's a selection bias, because events with positive chi effective are more detectable. So you have to sort of downweight them because you explode more of the universe to get to them. So that is the second panel. And even after doing that, there seems to be an excess at positive chi effective. But so this is just a way to explore the distribution visually before doing any Bayesian model selection, because we sort of wanted to see what was in there. And from our eye, it seemed like the distribution seemed like there was a part which was consistent with 0 chi effective, and there was some part with positive chi effective. And then we can go and throw the full Bayesian sort of model selection at it, using the methods which are very similar to what were done in the LVC analysis. And the only difference being we are exploring a different parameterization of the effective spin parameters distribution. So motivated by our, in what we saw, we sort of modeled the distribution as having a part with effectively 0 intrinsic spin, which is this bump here. And then we are interested in seeing are there negatively spinning events in there, or are there positive spinning events in there, and what is the relative number. So then we sort of put in by hand two half Gaussians with different allowed amplitudes, and then fit these numbers through the observed distribution. So this is like the morally correct way to do it, even though it's more complicated, because you have to do a formal model fitting, but this fully accounts for this selection effects that you might have in the sample. So after doing this, we found that interestingly, at least from the catalog that was there in the O3A, after O3A, the data, so this is the posterior for the positive fraction and the negative fraction, and the spread for the Gaussians. So the posterior for the negative fraction is consistent with 0, while the positive fraction has, is measured to some number. And if you look at the positive equals negative, which is the diagonal line there, it seems to be shifted towards the positive part. And we can also so the model that was fit in the official LVC analysis was just a Gaussian with a free mean and a free spread. So when we restricted ourselves to that model, we reproduced the LVC analysis. So just to make sure that we are not doing something incorrect. And we can, but then the Bayesian analysis also comes with a number which tells you which fit is preferred by the data, which is the evidence. So the evidence mildly favored this scenario, the scenario where there were basically no negative spinning events in there, and there were positively spinning events in the data. But I wouldn't say that I would stake my life on it, because there weren't that many events there. But like when we get more events, this should become sharper, and maybe we can rule out or confirm it. Yeah, so it's like 1.5 units of evidence, whatever you make of it. Okay, so
okay, maybe you want to leave. This is the last slide, or
so that after this there is just the conclusion. So maybe we can talk about this if there are no questions. I'll just leave the interesting future directions up here.
Okay, thank you very much, Teja. Very good. So let's have some questions.
There are some questions here in the room.
Okay, and there is a question from Sate. Yeah, so let's have first the one from the room.
Hello. Yeah, thanks for the nice talk. So you mentioned this one event that had precession and evidence of higher harmonics. So could you say a little bit about the waveform models you're using to do that, and whether you tried multiple waveform models and how that makes a difference, and the parameters you get for the
Yes.
precession
So
and-
unfortunately, we only tried the IMR phenom XPHM model, which we could call using LAL. I know that there are other models. I don't think we have results with the other models, though they might be on disk. So I have to check.
Okay, thanks.
I mean, if you have reasons to believe that some other model is better, we can check that.
So I have a follow-up to that, if it's all right. What you said, this has evidence of these higher harmonics in orbital precession. Did you quantify that evidence in some fashion?
Yeah, so we're in the process of putting out like a P release, and that will have all these numbers.
Okay.
But I can give you a rough number that the amplitude of the Z of the 3,3 relative to Z of 2,2 is like 10% or something.
Thank you.
Okay, let's have the question from Satya.
Thank you very much for the nice talk, Tejasvi. I have a couple of questions. Staying on with this plot, you have the mass ratio Q.
Yeah.
I think, those are there two different waveform models? I'm sorry, I could not quite, I got cut out.
So the orange distribution is for just the phenom D. So
okay, I see that now.
It has no precession or higher harmonics.
Okay.
And the blue one has both.
Okay, all right. So if you have large mass ratio like this, it is possible to have higher harmonics. But did you measure the signal to noise ratio in any one of these? You show 3:2, 2:1, all of these are used, but do you have relative measure of these things?
Yes, so I think you are correct that what I showed here is not necessarily measurable on this plot, because this is just the predicted 2:1 or predicted 3:3 from the parameters that we have.
That's right.
But I think, so I think we have evidence numbers, though we did not put them in the graph. But I was saying to Aaron that roughly the 3:3 I think has roughly like a tenth of the amplitude in terms of Z. So not in terms of H, but in terms of, you know what? Yeah.
Okay. My question also concerns the number of detections you made. So from your paper, I see that you did not detect 3 of the confident events of the LIGO.
This is to be expected at this point.
I completely agree. That's not a criticism. The LIGO Virgo Kagra collaboration did not detect this the 10 additional events. What I was going to ask about was, did you find what the reason are? I think you just mentioned it was below the threshold. I wanted to better understand, because this is a part of the parameter space where I would have thought it's a good region, but I wanted to understand from your point of view what was.
I can give. Okay, let me answer the first thing about why some of the LVC, very loud LVC events are not in our list, which is because we set very aggressive vetoes. So it is to be expected that at some point we start throwing out real events. And I sort of expected to see that in the previous run already, but I guess we got lucky there.
Yeah.
And now we are starting to see it. So then it becomes a question of what are you looking for? So if I want to promise that I really will detect every loud thing, then I would set the vetoes to be very weak. If I want to really detect as many events as possible with some small chance that I lose a real event, then I would be very aggressive, and we went the second way. And you can decide what you want, I think, in the long run. And the second thing is why these events are not in the LVC list. So obviously, I cannot answer that because I don't have access to the LVC lists.
No, some of them are in the subthreshold.
Yes, that was not. But I don't have the subthreshold list.
You're right. Yeah, maybe. maybe we need to look at that.
Should have been released. We'll have to check.
Oh,
on
it
that.
was released, I think.
Yeah. Oh, the full trigger lists were released along with both papers, so
I see.
they should be out there, downloadable from Zenodo. But we can
I see.
discuss
So maybe I missed
offline
that
about
because okay, I did see the OGC list, which is another search that is done by CBC, and I think they were there in the OGC list down there.
Yeah, they were just some threshold events. Yeah. Okay. Thank you.
Any other question?
Yes, thanks for a very nice talk, Teja. A couple of questions actually related to Satya. So one is you have described very nicely that you have to make a choice about how you weight different templates effectively, right?
Yes.
And my question is your choice motivated by just increasing the total number of detections or detecting more things of the kind you've already seen? Or instead, you could say, well, actually, we've seen enough binary black holes. I'm interested in seeing neutron star black hole binaries, so I'll weight those templates more heavily.
Yes,
so how do you make the decision?
that's a choice you can make. And we went in the choice of our priors were like a power law in masses and flat in chi-effective. If you wanted to really say, I only want to see things that we have seen, then you could downweight the negative chi-effective part and you could play with that and get some more maybe out of it. We wanted to see if there were any, interesting things out there. So we tried to be as agnostic as possible. So the main point of the power law is to cancel the phase space, the template phase space that I mentioned, but we tried not to be very picky beyond that. But yes, you could play the game of, I really want to see everything that is like the things I have seen before. Then you could get some more, I think.
And if I may, one more related question. So as you described, there are some differences in the tuning of your search, for example, versus the LBK searches. Yeah. One could imagine creating other searches with other tuning choices. At some point, do you worry about a trials factor in the sense that, now if we just fold together all of the claimed detections from different searches, of course, the confidence in any individual detection should start dropping, especially for those things which are only detected by one search, not another. So should we start somehow accounting for that?
I think you're getting to a question which is sort of politically charged. So, because then, okay, you could ask, you should really then weight by the sensitive volume, you should do something. And I think to date, there has not been beyond just running them on the same data. We have not had much crosstalk about putting them together and really getting to the root of what could be changed to do what. We have had some conversations and maybe it will happen, but it's a slow process, as you can imagine.
Thank you.
I had a rather somewhat technical question about your Piastro that just occurred to me. But by the way, thanks for the great talk and also the great work. I actually enjoy always seeing these new ways of the data being handled. But the Piastro, when you calculate it, does it focus on the parameter space region that each sub-template bank is related to? So in other words,
the Piastro is an intensive quantity, so it does not depend on the rest of the search. For a given region of parameter space, the Piastro is the ratio of the background rate and the signal rate. Or vice versa.
Within that template subbank. So it's
not even within subbank, but yes,
so it's different. Its definition is quite different than the LVK definition because it actually goes across the entire mass space.
I think you're talking about the false alarm rate because the Piastro in the LVK is still you have a signal distribution in there. So that will focus on so you're talking about for each thing, you're also including the uncertainty in the intrinsic parameters.
Maybe we'll talk offline. The denominator in LVK includes all the regions.
Yes. So if you want a number which is, so the Piastro that we report in the search is kind of approximate because we don't have a marginalization over the intrinsic parameters in there, but we maximize over them. So the marginalization we reported in our population paper, and so the numbers are more or less consistent for most of the events, and they will fluctuate for some of the events as you would expect. Yes, but I don't see any huge differences.
Okay, is there another quick question? Otherwise, we stop here.
That's one. And one question on your last slide. Can you show it? So, okay, the second bullet, I read fast through it, and I would think the deeper you go in the spiral phase, the more control you have. So what do you expect any problem to be there?
Sorry, I could not make out your question. Maybe.
Didn't hear?
It was not clear to me.
Okay, the second bullet, you see that
Yeah.
in the BBH, if you see more cycles in the low frequency,
Yeah.
you think that current waveform models are not good enough.
I'm not thinking, I'm asking.
Okay.
Because everyone here is an expert in waveform
What
models.
makes you think that there can be a problem when neutron stars are detected with thousands of cycles?
Well, the neutron stars cycles are much less relativistic than the binary black holes. You don't even see the merger. So I'm talking about the part. So the point of this question, I think, which is partly answered by one of Christopher's slides actually, is in current waveform models, you often glue together a merger ring down model with an in-spiral only model, right? And these are so that you can describe the entire signal. So it's more a question of, are you sure that the gluing is correct even if I go down to very low, if I have many more cycles at low frequencies?
I would think it was better, but maybe other people can.
Well, because you have calculations up to some post-Newtonian order, and when you have higher terms, they'll get you closer to the merger. So I was asking, do you have enough terms to get to the point where you can match to a numerical relativity waveform? So it might be that it is immediately obvious to you and I'm incorrect. I was just asking the question.
Well, I think what Stefano perhaps is alluding to is that if you go to lower and lower frequency, the post-Newtonian or the analytical models in general based on post-Newtonian are going to be more and more accurate. So that's the expectation. But it's true that there could be some small error, and if you have more cycles, many more cycles, it may give an accumulated, could accumulate and give you a larger error. This is maybe what you are wondering, because the matching to numerical relativity merger is more at high frequency. So it's not actually related to your question here, I think.
Well, okay.
But anyway, people do consistency check, try to understand, by comparing different way of writing, of developing this waveform model, if they agree with each other at low frequency. There are parts of the parameter space that are more delicate about this, and I'm sure that people are going to look into this as the number of cycles will increase over time. Any other question? Actually, no, because it's already 10:35. Sorry, I didn't see the time. So now there is a break until your local time, 11 o'clock. Let's thank Teja again and the other speaker, and see you in 25 minutes.